Let's get started. I have something great for you guys today. Let's do a quick recap of everything that we have talked about so far. So this is sort of like a quick review, and then after this big picture, I will do some practice problems at the end of today's lecture. So let's think about from the beginning of the quarter to now what we have talked about. We started with the concepts of, we studied some examples of control systems, and then we talked about the basic concepts of what is a system. In particular, for our case, a system can be not controlled or controlled. For our case, we focus on control systems. So there are these concepts of what does it mean for a system to be linear or non-linear? What does it mean for a system to be dynamic or static? Right? And then what is the meaning of causal system and acausal system? Time invariance or time varying systems. And then the concept of open and closed loop, and what are the benefits of each of them, which is usually characterized, which can be usually described in a block diagram. So these are all the basic concepts of a system that we talk about, and it's useful for you guys to have a good grasp of these concepts during practice or exams. So these are roughly abstract. Some of them you can have mathematical tools to validate whether it's a causal time invariant or not. Now, when we move on to the more mathematical descriptions, we want to describe a system. We brought up the concept of a model. These are usually mathematical descriptions, and for our case, it's usually ordinary differential equations or ordinary difference equations. So they are characterized in continuous time and discrete time systems. So continuous time systems, we studied the tools. This is starting from what you are more familiar with, the transfer function approach. We studied the tools of Laplace transform to describe a model in a transfer function format. So it is important here to understand what is the definition of a Laplace transform, what are their properties, and what are some of the common pairs. So we have a table in the notes, and you can feel free to use that table in exercise or exams. And then similarly for Z-transform, this is for discrete time systems, and in the textbook, in the reference textbook, it's in section 2.8. For this one, it's in chapter 2, most of the concepts here. So we similarly have the definition and properties and common pairs. These are usually you can build a good analogy between these two to establish a transfer function. Now, Laplace and Z-transform are useful not only for deriving transfer functions, but also it is useful when we talk about state space systems. The concept of a state and why it is useful for complex systems is we covered in class, and it's also in section 4.4 and 4.5 in the reference book. So we talked about now you can go back and forth. If you have a state space description of a system, of a model, then you can go from here to a transfer function to obtain a transfer function. We talked about the concept of if you have the BCD matrices, then there's only one way you can go. So it's unique. Giving you a state space description, the transfer function of a system is unique. Then backwards, this is our content for last lecture. If you have a transfer function and then you want to obtain the state space description, so this is so-called realization problem. I want to realize the transfer function using state space. So then it is no longer unique. There are canonical forms: controllable, observable, Jordan, diagonal, or modified canonical forms. So there are different realizations. It's no longer unique. Go from the left to the right, and then we will finish up that part by talking about what are the relationships between these realizations today. So once we have the model established, we can think about response. We can think about what the model will generate as an output. So this is the topic of today's lecture mostly. So we already know if you have a transfer function, so there are these response, impulse response, step response, DC gain, and then actually you can try all kinds of inputs to the system in MATLAB. So this concept of response of a transfer function is relatively well established. So you know how to obtain that, and you have tools to simulate that. Now, if you have a state space system, then same thing. You can talk about the response of the system. And this is the topic for today. And in the reference book, it's 4.1 and 4.2. So that's the big picture. Now let's start from here, continue what we have left at the last lecture. So let's do an exercise. We talked about, we spent time to derive the continuous time canonical representations. And we built this concept that in discrete time, the same ABCD matrices and the same block diagrams will apply. So let's take a look at this one. Discrete time system, third order, asking for the controllable canonical form. You guys have had some thoughts on the problem. Let's work on this together. So first of all, we know how to do this if you have, this is our demo problem, right? So we know how we provided ABCD matrices for this transfer function, where the coefficients are ordered like this. So for this one, the first step that I would do is to translate this form, this transfer function, into a structure that looks like this. So I see this is using z to the power of -1, -2, -3. So I will translate to this format and obtain, so I multiply, I see the highest order is z to the power of -3. So I multiply z to the power of -3 and get this in the denominator, and in the numerator I got 1. So that's my first step. And then the difference between these two is just a notation difference. This is using z, this is using s, and then nothing else. We know how this controllable canonical form looks like. There are formulas for that. So the formulas for this one is A is what? 0, 1, 0, 0, 0, 1. And then what is sitting here? -A2, -A1, -A0. And for B, controllable canonical form is 0, 0, 1. And for C is what? And D is 0. So that's the controllable canonical form for the standard system, general system, third order system. So for this one, just plug in, figure out what is A2, A0, etc. So for this one, I got A is 0, 1, 0, 0, 0, 1. And then at the bottom, my A2 is 2, right? So it's -2, -1, and then 0. That's my A matrix. B matrix is amazingly simple in controllable canonical form. C matrix is, take a look at here. So B0 is -1. B1 is, there's no term of z to the power of 1, so it's 0. And then B2 is 1. And then D is 0. So that's a controllable canonical form that I got. All right? if you practice a little bit more times, then you will find the structures actually make sense. So what did we talk about? What is the, let's do a comparison. What is the observable canonical form for this one? For this transfer function. So this is controllable canonical form, observable canonical form, A, B, C, D. D is 0. That's easy enough. So the observable canonical form is 0, 1, 0, 0, 0, 1. Then what are the things here? So it's I had a typo. Negative A2, negative A1, negative A0. And then the observable canonical form is 1, 0, 0 here for C, and then B2, B1, B0. So these are from the last lecture. We talked about one intuition for the observable canonical form, right? What did we talk about? We said the output y, right? Because C is 1, 0, 0, so y is just x1, right? So the output directly observes one of the state. And then from the observed state, we can infer like how other states look like. So that's one of the intuitions we can make here. Now, take a look at this one here. What are we observing from the structure? What does it mean for B to be 0, 0, 1? So my control action is what? It's acting on which state? X3, right? So my control action can directly act on one of my state immediately. And then, so X3 is being directly accessed in my control input. Now, how does X2 depend on X3?
X2 dot is X3.
X2, the derivative of X2 is X3, right? If my control can directly impact X3, then X3 sort of impact X2 also, right? X2 is just integration of X3. So similarly, once I influence X2, then X1 is impacted. X1 dot equals X2. That's how the controllable canonical form makes some sense over here. Because my control is impacting my states, and then sort of in this sequential format, X3 is controlled, X3 influences X2 directly, X2 influences X1 directly. So therefore, it's controllable. So we will put these concepts into more rigorous mathematical descriptions later. But here are something that you can observe. Observable canonical form always have this simple form in C. Controllable canonical form always simple in B. So that's this example. So just to recap, we also derived the block diagram over here. This is for the continuous time case. We figured out how x1, x2, x3 can be arranged in this format. So we always check this integration item over here. Around the integration, after it, we define the states. If we have a discrete time system, what will change in here? Huh? Yes, so for discrete time system, the only thing that changes is change this with Z. That's the notation difference between these two. So everything else are the coefficients, the location of these coefficients are exactly the same. Cool. Now, we have cleared up the different canonical forms. Let's talk about the relationship between them. One of you guys asked the question of, if I have a controllable canonical form, can I go to Jordan form or some of the diagonal forms from the ABCD matrices? And the answer is yes. How do we do that? Is on this slide over here. We talked about how a matrix transforms a vector space to another. So if you multiply a vector x star by a matrix, it's just transforming the state to another kind of state representation. Let's do that. Let's say I have a state space realization ABCD. So these are the state equations. So the state under this realization is X. We can choose, let us choose a new set of states, and it's defined by this matrix T. So I'm defining a new state, X star, as following. X is equal to T times X star, and T is invertible, is a non-singular matrix, it's invertible. So we will be looking into like what kind of T this is to do some of the, let's go from continuous time, let's go from controllable to diagonal later. But for now, let's say this is just some transformation matrix. I'm going to transform the state space from X to X star. So let's see what will be the corresponding ABCD matrices for this choice of state, X star. All right? So that's the basic idea we're going to be pursuing. To actually move on to the mathematics, let's take a look. So X star equals AX plus BU. That means just plug in the definition here. So that means X star is T times X star taking the derivative. And T is just a constant matrix. It doesn't depend on time, so you can take out T and then obtain the derivative of this new state X star on the left-hand side. And on the right-hand side, you have A times X of T is capital T times X star plus B times U. So T is an invertible matrix, is non-singular. So we can multiply the equation by the inverse of T on both sides. I get, on the left-hand side, I get rid of T. So T inverse times T cancels out. And on the right-hand side, I got T inverse times AT plus T inverse times BU. Similarly, we have y equal to cx plus du originally. So in this new form, we got, just to replace x with t times x star over here. Now, this is talking about how x star, the derivative of x star, depends on itself. Let us call this, let's say, lambda. This is the new matrix for this choice of states. And this is the new B matrix. Let's call it B star. And then this is C times T is the new C matrix. And the D matrix remains the same. This is called a similar realization to the original system under a different choice of state. Any questions? All right, so now let's go back to revisit a concept we reviewed in linear algebra. So at the end of the linear algebra lecture, we talked about the concept of diagonalization, right? We can go from one general A matrix to a diagonal matrix. And that diagonalization depends on the eigenvalues and eigenvectors. So now, let's get some perspective from this similarity transform. Given me ABCD matrices that can be complex for a general system. For this one, it might be difficult to directly work on, right? A can be complex, can be square, can have elements that are complex. It can have something here, something here, something here, something here. So it's not easy to visualize the relationship between the states if A has elements sitting around everywhere, right? So in this case, x1 star will depend on what? Will depend on both xy and x2. Now, if this is diagonal, what will be happening here? If this diagonal, if somehow we manage to express the system in an entirely diagonal way in the A matrix, x1, x2, then there can be B matrix and U here. Then you can see it's very easy to visualize what's going on. x1 star depends only on x1, and x2 star depends only on x2. So we have decoupled the two states in the system model. You all know how to solve like ordinary differential equations that look like this, right? It's amazingly easy to solve if you have x1 dot equal to lambda 1 x1 dot plus, let's say, b1 dot times u. This ordinary differential equation is the easiest to solve. First order, no other variables. That's easy to solve. We will be using this result again. We'll revisit this result when we talk about response, when we talk about the response of a state space system. All right. With that, let's take a look at this little exercise. So I give you two realizations. ABCD matrices are like this. So in the packed representation of a model, this is A, B, C, D, A, B, C, D. I would like you to verify that these descriptions are for the same system. It's the same transfer function for these two systems. So take a look at the two representations and see how we can prove this quickly. Okay, what do you guys think? Yes?
You just switch the order of x1 and x3.
All right. So it is a little bit not so clear from the ABCD matrices directly, but if you write out actual system equations, you can see this is for the first system. So x1 dot equals negative a2x1 plus x2 plus b2 times u, and x2 dot is negative a x1 plus x3 plus b2u, so on and so forth. So you can write it out. And then do the same thing for this system. And then you realize what? The states are sort of very well connected. The second equation is exactly the same. And the first equation for the second system realization is what? It's very similar to the third equation here. You can see the connection exactly over here. So if you do let's do x1, x2, x3 for the first system, and then let's consider the new system states. right? So you can see they are connected by what? What kind of matrix here? So x1 is becoming x3 in the second system, right? That means is 0, 0, 1. The second state is exactly the same. And the third state becomes the first state in the system. So this is the T matrix in the similar realization that transforms one choice of states to another set of states. And then what did we talk about for the condition of T to make it a similar realization?
Invertible.
T must be invertible, right? So because you can see this is invertible matrix. This is indeed, so this defines a similar realization. So therefore, these two systems are exactly the same system. Yes?
Sorry, can you describe what is the definition of two similar systems? What properties do they have to have in order to be the same?
Right, that's an excellent question. So the property for them to have is, in the end, they're going to have the same transfer function, right? So I will show you in a minute. I can do it here. They're going to have the same transfer function. And then they're going to have also the same, because the transfer functions are the same, so the poles, the zeros, are all the same. Okay, so the impulse response, step response, all the same. Just the choice of states are different. Now, let's go back and talk about the relationship and justify that if I do this, the transfer function does not change. All right? So here is the realization that we went through. Now, in the original system, ABCD, so the transfer function would be CSI minus A inverse B D. Now, if the new ABCD matrices are, let's say A star, this is our lambda over there, is T inverse AT, B is T inverse B, C is CT, D is the same. So let's see what is the transfer function if I use these computations. So it's going to be C star Si minus A star inverse B star plus D star. So let's see. D star is very easy. It's the same. So we have some good start. So there's some good news to begin with. C star is C times T. And then Si minus A star is T inverse AT. And then the whole thing taking an inverse. B star is T inverse B, and then D. So it looks promising, right? I see T and T inverse, so there are potentials to cancel things out in between. So be a little careful now. From here, I can see that I can do this. I can do T inverse Si T for the first term, because I see the structure here. And then do minus T inverse AT. So I can take out T inverse, and then Si minus A T. Any questions so far? do inverse on the entire thing, what do we get? So the whole item getting an inverse. Let me call this star. Star inverse is what? Let me actually write it here, easier. So if you have three matrices multiplied together and you take the inverse, what do you get? It's taking individual inverses and then flip, right? So it's going to be T inverse Si minus A T. Right? So then what? After you do the multiplication, this T cancels out with this T inverse. This T inverse cancels out with this T. So they are exactly the same. Any questions? Yes? The one in the back?
So why are we doing all this T inverse and T multiplication? Like, what's the purpose behind this?
Okay, cool. What about you?
I just wanted to ask, we found the T matrix. Can't we just take T inverse AT and just say that this matrix is same as the A matrix, so it is valid?
You repeat the question. So we have T.
We have T.
Right.
And so from that we can find T inverse AT, which is the first block of the exactly. So instead of doing it algebraically, we could substitute the matrices and can we just use the numbers? Will it lead to the same solution?
So your classmate's question at the beginning is trying to verify that these two transfer functions are the same. So if you work on this part, you're only going to be able to conclude on the A matrix.
Okay.
And
The same for, okay.
yeah, even if you have the same A matrix, you cannot directly conclude the transfer function is the same.
But we could repeat the steps for B and C as well, right?
You
We have
can.
the T and we have the T, we have C. So.
You can. Yeah, you probably can. But I guess it's maybe we'll have to be a little bit more careful. So you can, if you think of it in a different way, you sort of now we have go through one similarity transform and got an ABCD matrix. So you can imagine if you do another similarity transform to go back, there's another set of T to allow you to go back from here to here, right? And then you can recover ABCD whatever exactly the same. But I guess that will be an overkill for this kind of exercise here. Yeah, so going back, let me address your classmate's first question. Why do we do the similarity transform, right? So you can imagine different scenarios. One of the scenarios is you may have, let's say, so I can erase this part at least. So you can imagine A, this is the same example that I talked about earlier. A can be complex. K can have some structure to begin with, right? Let's say like this. So by similarity transform, we can make it to diagonal, for example. And then things become easy. So diagonal means diagonal realization or Jordan form realization that we talked about. And this can be general A matrix. So there are two more questions, one from the back and then another from the front.
Yeah, it's just a simple notation question. At the bottom right-hand corner, you're saying T inverse times S I minus A times T, and you're calling that star.
Yes. So
and then at the top, you're saying the inverse of star is equal to, I see.
right, yeah. Yeah, so the whole thing, I call it star. And then I do the inverse over there.
Okay, thanks.
Should the Si minus A term on star be inverse?
On the top.
On the bottom. Should it be T inverse Si minus A inverse times
T
T?
inverse Si minus A inverse. This one? Here should be an inverse? I mean,
I think. Well, I'm not sure if it's there or there, but when you plug it back into the G of S equation,
okay.
I feel like I'm missing an inverse part.
Okay, cool. So let's rework on this a little bit and make things clear. So we have this big chunk of matrix multiplications I need to work on. So I said, let's take a, this is the biggest thing that we need to tackle. This whole thing inside, I work on it here. And then after I finish, I do the inverse. I consider the inverse of the whole thing in this step. So all the computation here is strictly for the terms inside this bracket.
Should the Si minus A at the top have an inverse on it?
Yes. That's the typo. Any other questions? Excellent. We talked about why we want to do this, what kind of convenience it can make. Right now, there are a few. You will see more for sure. But one thing is clear. These two are the same realizations. So in the textbook, in the reference, it uses this as the observable canonical form. So you can see that they are exactly the same. The difference is a notation difference. So in this case, C is 0, 0, 1, so the output Y equals to X3 instead of X1. But the concept is the same.